Hello friends, I welcome you in lecture number 2 on roots of equations. In this lecture, we will discuss one question on bisection method which was asked in GTU Winter 2019 exam of Applied Mathematics for Electrical Engineering subject. In previous lecture, that is in lecture number 1 on roots of equations, we have discussed about bisection method, that how that method works in finding approximate root of the equation fx equal to 0. So now we are familiar with the process of bisection method. It is an iterative process and our aim is to find out approximate root of the equation fx equal to 0. So using bisection method, we will try to solve this equation x minus cos x equal to 0 in this lecture. Question is, find a positive root of the equation x minus cos x equal to 0 using bisection method. Correct up to 2 decimal places or 2 places of decimals. So whenever they ask you to find out your answer correct up to some decimal places, then you can fix your calculator up to required decimal places or more decimal places. So here you are asked to find out root up to 2 decimal places. So you can fix your calculator up to 2 or 3 decimal places, and at each iteration you can verify your answers, successive answers up to 2 decimal places. When the 2 successive answers agree up to 2 decimal places, we can stop our procedure and we are able to find out the solution correct up to 2 decimal places. So first we are writing the given equation, which is x minus cos x equal to 0, and if we compare with this fx equal to 0, we have to consider function fx as x minus cos x. Now what is the bisection method? Bisection method says that if your function is continuous and if you can find out two real numbers a and b such that value of function at those 2 points is of opposite sign, that is you can find out 2 points a and b such that f of a is positive and f of b is negative, or you can find out 2 points a and b such that if f of a is negative then f of b is positive. So the first step in bisection method is to find out the interval which contains the root of given equation. So that we can find out by trial and error. We can consider particular values of x in this equation and we can evaluate our function at those points, and we will search for those points a and b for which either this or these conditions are satisfied. So I start by taking x equal to 0 and I find that f of 0 turns out to be 0 minus cos 0. Cos 0 is 1, therefore value of function at x equal to 0 is minus 1, or f of 0 is negative. Now I can try for x equal to 1. So if I take x equal to 1, I have 1 minus cos 1, which turns out to be 0.46 and it is positive, therefore f of 1 is positive. So we have obtained 2 points 0 and 1 such that function is of opposite sign. Therefore by intermediate value theorem we can say that our root must lie between 0 and 1. So this is the search interval for root of this equation. And here we have cos x, which is trigonometric function. So while doing all these calculations, we will consider radian mode. Keep your calculator in radian mode for evaluating this type of trigonometric functions. And here our answer is required correct up to 2 decimal places. So I have done all my calculations by fixing my calculator up to 3 decimal places. Now once we find that our root lies between 0 and 1, then first approximation to the root is nothing but midpoint of this interval, that is this point. So that is average of 0 and 1, and that is 0.5. So this is our first approximation to the root by bisection method. So that I have written here. Therefore, the first approximation to the root to the exact root is x1 equal to 0 plus 1 divided by 2, that is 0.5. Now we know that f of 0 is negative, f of 1 is positive, and now we evaluate function f at 0.5. We find out value of function at 0.5 and we find that f of 0.5 turns out to be minus 0.378, that is negative. F of 0.5 turns out to be negative, that means in this direction. F of 0 is negative, so we can show by this type of arrow, and f of 1 is positive here. So we find that f of 0.5 is negative and it is average of 0 and 1. So I have to check whether for which point function is positive. F of 0.5 is negative, so I have to check whether function is or I have to find out the point out of these 2 points for which function is positive, and we know that f of 1 is positive, and from this also you can decide that f of 1 is positive, f of 0.5 is negative. Therefore now we are sure that root cannot lie in this part because f of 0 and f of 0.5 are negative. So our search interval is reduced here. Now our root is in between 0.5 and 1. So now I have written that f of x1, that is f of 0.5, is negative and f of 1 is positive. Therefore the root lies in interval 0.5 to 1. Therefore the second approximation to the exact root is average of 0.5 and 1, that is 0.75. So now we consider next approximation as midpoint of this interval. Midpoint of the interval 0.5 to 1 is 0.75. So now our root lies in this interval 0.5 to 1 and midpoint of this interval is 0.75. That is our next approximation. Now we will repeat this procedure. We will find out value of function at 0.75 and we will see whether it is positive or negative. So we have obtained f of x2, that is f of 0.75. 0.75 minus cosine of 0.75, that is positive. F of 0.75 is positive, so I can show by this arrow, and 0.75 is average of 0.5 and 1, and f of 1 is also positive. So now we can discard this possibility. Root cannot lie in this interval because 0.75 and 1 at both of these points function is positive. So our search interval is now this interval 0.5 to 0.75. So I have written here that this is f of 0.75 is positive and it is average of 0.5 and 1, and f of 0.5 is negative. Therefore root lies in the interval 0.5 to 75, and the next approximation is average of 0.5 and 0.75. That turns out to be 0.625. So this point is now 0.625 and that we have denoted by third approximation. So this is our x3. It is 0.625. So again we find out value of function at 0.625 and we see that it is negative. So we can see that f of x3 is negative and f of 0.75 is positive. Therefore now we can discard this possibility. Now root lies between x3 and 0.75. So that we have written here also. F of x3, that is f of 0.625, is negative and f of 0.625 is negative and 0.625 is average of 0.5 and 0.75 and function is positive for 0.75. Therefore, next interval is 0.625 to 0.75. We are not considering 0.5 because f of 0.5 is negative, and therefore the next approximation is average of 0.625 and 0.75, which is 0.688. So that is this point. Midpoint of the interval x3 and 0.75 is x4. So we repeat this procedure. So here I have written that this root lies in this interval 0.625 to 0.75. Therefore, next approximation x4 is average of 0.625 and 0.75, which is 0.688. Again we evaluate our function at 0.688 and we find that function is negative at 0.688. So we check that out of these 2 points for which point function is positive, and we know that function is positive for 0.75. So f of 0.75 is positive, f of 0.688 is negative. So next approximation is average of 0.688 and 0.75. So I have written that therefore root lies in this interval, and therefore x5 is average of these two, which turns out to be 0.719. Again we find out value of function at 0.719 and it turns out to be negative. 0.719 is average of these two and value of function is positive at 0.75. So next search interval becomes 0.719 to 0.75, and next approximation is average of these two, which is 0.735. And be careful, we have to compare successive iterations every time. We can see this is 0.719, so if we round off up to 2 decimal places, this is 0.72, and if we round off up to 2 decimal places, this turns out to be 0.74. So they do not agree up to 2 decimal places, so I have to search for next approximation also. So for that, again I obtain value of function at this point, it is negative, and this 0.735 is average of these two, and we know that function is positive at 0.75. So next approximation is average of 0.735 and 0.75, that is 0.743, and if we round off up to 2 decimal places, this is 0.74. So x6 and x7 agree up to 2 decimal places, and we are asked to find out root up to 2 decimal places. So therefore we can stop here. 0.74 is the root of given equation correct up to 2 decimal places, because x6 and x7 agree up to 2 decimal places. So this is very easy method. We have to just start with 2 points A and B, then we bisect this interval, and whatever midpoint we obtain, that is x1, and suppose f of A is positive, f of B is negative, and if f of x1 is negative, then root cannot lie in this interval. Our next search interval become A to x1, so we again bisect that interval, and midpoint of that interval is next approximation. Suppose value of function at x2 is positive, then root cannot lie in this part. So next search interval is x2 to x1, and we consider midpoint of that interval as x3, and we continue in this way. So this process is very slow, but we are sure that we will get our answer which is convergent to the exact solution. So in this way we can apply bisection method to obtain roots of nonlinear equations, and here we find that positive root of this equation x minus cos x equal to 0 correct up to 2 decimal places is 0.74. So this is all about this session. I hope you like it. If you have any questions, you can ask me in comment section. Thanks for watching.